Planet X, -99Z4, an enigmatic celestial body adrift in the vast, uncharted depths of the cosmos, has ignited the curiosity of astronomers and space enthusiasts alike, challenging conventional understanding of planetary formation, atmospheric dynamics, and the very nature of existence beyond our solar system, as it appears to defy categorization, exhibiting characteristics that align neither with terrestrial nor gas giants, prompting numerous theories ranging from the plausible to the utterly speculative, each vying to explain the planet's hauntingly unique features, particularly the colossal eye-like structure that dominates its surface, giving rise to eerie conjectures about artificial megastructures, ancient extraterrestrial civilizations, or extreme geophysical phenomena unseen anywhere else in the known universe, with some scientists proposing that the supposed eye could be the result of an immense impact crater reshaped over millennia by relentless erosion, while others argue it might be a highly unusual atmospheric vortex, a storm so vast and stable that it has persisted for eons, much like Jupiter's Great Red Spot. Yet the absence of a parent star further complicates matters, as rogue planets, which drift aimlessly through interstellar space, are often assumed to be barren, frozen wastelands, utterly inhospitable, and devoid of the essential ingredients for sustaining life. Though new models suggest that internal geothermal activity, driven by residual planetary heat or tidal forces from an unseen massive body, could allow for subterranean oceans beneath an insulating icy shell, much like the hidden seas suspected to exist beneath the frozen crusts of Europa or Enceladus, raising tantalizing possibilities about alien life, albeit of a form radically different from anything found on Earth, possibly thriving in darkness, feeding off chemical reactions instead of sunlight, fueling speculation about hydrothermal vent ecosystems where extremophiles, organisms that can survive in extreme environments, might have evolved in complete isolation from the rest of the galaxy. Yet the odd gravitational anomalies detected near X-99Z4 suggest the presence of an unseen force, potentially an undiscovered moon, or even a nearby black hole, warping space-time in its vicinity, an idea that, if confirmed, would place the planet within one of the most extreme environments ever studied, forcing scientists to reconsider long-held assumptions about planetary survivability in deep space. And although telescopic observations have provided crucial data, the true nature of the planet remains an enigma, as no spacecraft has yet ventured close enough to capture direct imagery or sample its atmospheric composition, leaving researchers reliant on spectral analysis and gravitational readings to piece together a fragmented picture of what might be one of the most unusual celestial bodies in our galaxy, leading some to argue that X-99Z4 could be the remnant of a once thriving planetary system, a world cast adrift after a cataclysmic event, such as a stellar explosion or an interstellar collision, a theory supported by the presence of fragmented debris scattered throughout its approximate trajectory, hinting at a violent past that may hold secrets to the chaotic forces governing planetary ejection, though others suggest that the planet might have formed independently, deep within a cold, dark nebula where starlight never reached, giving birth to a planet entirely unlike those familiar to humanity, with conditions so extreme and alien that they defy all conventional planetary classifications. Yet perhaps the most perplexing question remains unanswered. If the vast, eye-like formation on X-99Z4 is indeed an artificial construct, as some speculative theorists have proposed, what intelligence could have created it, and for what purpose, with some believing it could be an interstellar signal beacon, a relic of an ancient race attempting to communicate across the void of space, a structure designed to withstand the erosion of time and the hostility of the cosmic environment, awaiting discovery by those advanced enough to recognize its significance, though skeptics argue that such interpretations verge on science fiction, preferring instead to focus on natural explanations. Yet without direct exploration, the mystery will continue to fuel the imagination, and as next-generation telescopes and deep space probes advance, perhaps humanity will one day unlock the truth behind Planet X-99Z4, uncovering whether it is merely a cosmic anomaly, a geological marvel, or an unprecedented discovery that could change our understanding of life, intelligence, and the very fabric of the universe itself. From the earliest times, humans have gazed at the sky, attempting to understand the structure of the universe, with the first systematic observations of the stars conducted by ancient civilizations such as the Babylonians, Egyptians, and Chinese, who meticulously tracked celestial movements to develop calendars, aid navigation, and align religious practices with cosmic cycles, laying the groundwork for early astronomical theories that often intertwined with mythology and spiritual beliefs, as seen in the geocentric model proposed by Greek philosophers like Aristotle, and later formalized by Ptolemy, which positioned the Earth at the center of the universe, with celestial spheres carrying the Sunday, moon, planets, and stars in perfect circular orbits, a view that remained dominant for over a millennium due to its alignment with religious doctrines and apparent compatibility with naked-eye observations. Yet as more precise measurements of planetary motion were recorded, inconsistencies in the geocentric model, particularly the retrograde motion of planets such as Mars, began to raise doubts, leading to a paradigm shift in the 16th century when Nicolaus Copernicus introduced the heliocentric theory, arguing that the Sunday, not the Earth, was the center of the universe, an idea that was initially met with resistance but gained traction as observational evidence accumulated, particularly through the work of Galileo Galilei, who, using an early telescope in the early 17th century, observed the phases of Venus, the moons of Jupiter, and the irregularities on the moon's surface, all of which contradicted the Aristotelian notion of celestial perfection and provided crucial support for the Copernican system, despite fierce opposition from the Catholic Church, which saw heliocentrism as a challenge to scriptural interpretations, leading to Galileo's infamous trial and house arrest, though his findings, alongside Johannes Kepler's laws of planetary motion, which described elliptical orbits rather than perfect circles, and Isaac Newton's formulation of universal gravitation, which mathematically explained celestial mechanics, firmly established a scientific foundation that ultimately dismantled the geocentric view, paving the way for the Enlightenment in modern physics, as advancements in observational tools, such as increasingly powerful telescopes, enabled astronomers to further refine our understanding of the universe, culminating in Edwin Hubble's groundbreaking discovery in the 1920s that the universe is not static, but expanding, based on his observations of redshifted galaxies, which provided empirical evidence for what would later become known as the Big Bang Theory, revolutionizing cosmology by shifting the focus from a finite, eternal universe to a dynamic, evolving one, a concept that was further solidified by the discovery of cosmic microwave background radiation in 1965. Considered the afterglow of the Big Bang, and a key piece of evidence supporting the notion that the universe originated from an incredibly hot and dense state approximately 13.8 billion years ago, setting the stage for modern astrophysics and cosmology, where contemporary theories such as dark matter, dark energy, and the concept of the multiverse continue to challenge and expand our understanding, while technological milestones in space exploration, from the Apollo moon landings to the deployment of the Hubble Space Telescope, and more recently the James Webb Space Telescope, have allowed humanity to probe deeper into the cosmos than ever before, offering unprecedented insights into the nature of galaxies, exoplanets, and the large-scale structure of the observable universe, which is defined as the portion of the cosmos that light has had time to reach us from since the beginning of cosmic expansion, a sphere spanning approximately 93 billion light-years in diameter, though the true extent of the universe remains unknown, leaving open fundamental questions about its shape, fate, and potential for life beyond Earth, ensuring that humanity's quest for cosmic knowledge continues to evolve with each new discovery. The universe, vast and unfathomable, stretches far beyond the limits of human perception, a silent expanse filled with countless galaxies, each containing billions of stars, planets, and possibly entire civilizations. Yet despite its sheer immensity, it remains deeply personal to us, for within its mysteries lies the story of our origins, our place in the cosmos, and the fundamental nature of existence itself, evoking a complex mixture of emotions: wonder, curiosity, fear, and awe that have shaped human thought for millennia, compelling us to look up at the night sky and ask questions that have no easy answers, questions that tug at the very core of what it means to be human, because to contemplate the universe is to confront both its beauty and its indifference, An infinite ocean where Earth is but a tiny speck, fragile and fleeting. A realization that can feel overwhelming, even terrifying. Yet, paradoxically, it is also deeply humbling. A reminder that despite our individual struggles, we are part of something much greater, something ancient and boundless, stretching across time and space in ways we can barely comprehend. And it is this duality, the awe of the infinite and the insignificance of the self, that makes the cosmos so profoundly emotional. For when we stare into the depths of space, we are staring into the unknown, into the possibility that somewhere, in some distant star system, another being might be looking back, asking the same questions, wondering if they too are alone, if their existence has meaning, if there is something beyond the void. And in that shared uncertainty, there is connection, a bridge between the known and the unknown, between science and philosophy, between knowledge and imagination. Because every great breakthrough in our understanding of the universe, from Copernicus shattering the illusion of an Earth-centered cosmos to Hubble revealing that the universe is expanding, has been driven by the same fundamental impulse: the need to know, to understand, to seek meaning in a reality that does not readily offer answers. And yet, in our relentless pursuit of knowledge, we are confronted with paradoxes that shake the foundations of what we think we know, such as the unsettling notion that most of the universe is composed of unseen forces, dark matter, and dark energy that govern its structure and fate, forces that we cannot touch, see, or fully comprehend, reminding us that for all our technological advancements, we are still standing at the edge of an abyss, peering in, trying to make sense of a cosmic puzzle that remains largely unsolved. And yet, instead of deterring us, this uncertainty fuels our desire to push further, to send telescopes into the farthest reaches of space, to listen for whispers from alien civilizations, to one day step foot on distant planets, because deep down, the mysteries of the universe mirror the mysteries within us, the fundamental questions of identity, purpose, and existence. For just as we seek to understand the stars, we seek to understand ourselves, and in doing so, we come to realize that the universe is not something separate from us, not some distant, detached entity, but rather an intrinsic part of who we are. Because every atom in our bodies was forged in the heart of a dying star. Every breath we take is a continuation of a cosmic process billions of years in the making. And in this realization, there is both comfort and fear: the comfort that we belong to something eternal, that the universe is in us as much as we are in it, and the fear that in the grand timeline of the cosmos, we are but a fleeting moment, our entire civilization a mere flicker in the vast darkness of time. And yet, it is precisely this impermanence that makes our existence so precious, that gives weight to every question we ask, every discovery we make. Because even if we are small, even if we are fragile, we are capable of comprehending the universe itself, of unraveling its deepest secrets, of standing beneath a sky filled with stars and daring to wonder. And in that wonder, in that courage to ask why, to push forward despite the uncertainty, we find meaning. We find purpose. We find a reason to care about the vast unknown. For the universe, in all its incomprehensible enormity, is not just a thing to be observed, but a story we are a part of, a story that is still being written. And that is why we must care, because the more we learn about the universe, the more we learn about ourselves. And in the end, that might be the greatest discovery of all. Have you ever looked up at the night sky and felt something stir deep inside you? A mix of awe and curiosity, a sense that there is something greater out there just beyond our reach. What if the mysteries of the universe aren't just distant questions for scientists and astronomers, but fundamental keys to understanding who we are and why we exist? The more we discover about the cosmos, the more we are forced to confront the limits of our knowledge, not just about space, but about reality itself. Because every new finding, from black holes to dark matter, from exoplanets to the expanding universe, shapes the very foundations of what we think we know. What if time itself doesn't work the way we assume? What if the nature of existence is far stranger than we ever imagined? If space is infinite, could there be infinite versions of you living different lives in parallel realities? Could there be civilizations out there, staring back at us from their own worlds, wondering the same things? Or are we truly alone in the vast, silent void? These questions aren't just theoretical. They have the potential to redefine our place in the universe, and challenge everything we believe about life, consciousness, and the fabric of reality. What if one of our telescopes, scanning the depths of space, one day captures undeniable evidence of extraterrestrial life? Would it excite you or terrify you? Would it confirm something you've always felt to be true, that we can't possibly be the only intelligent beings in an endless cosmos? Or would it shake the very foundations of how we define life, intelligence, and our own significance? Or what if the opposite is true, and the more we search, the more we realize that we might truly be alone, that Earth is the only island of consciousness in an otherwise lifeless universe? Would that make our existence more precious, more miraculous? Or would it fill you with existential dread, knowing that the only voices that will ever speak, the only eyes that will ever look upon the stars with wonder, are our own? These are not just philosophical exercises. They are real possibilities. And each new technological breakthrough brings us closer to answers that could change humanity forever. Imagine a world where we have confirmed the existence of a habitable exoplanet, a second Earth orbiting a distant star. How would that impact our collective imagination, our sense of hope, our vision for the future? Would it ignite a new era of exploration, a cosmic renaissance where humanity finally embraces its destiny as an interstellar species, reaching beyond the confines of our fragile world to touch the stars? Or would it divide us further, with some seeing it as a reason to abandon Earth, while others insist that our focus should remain here, on solving the problems we already face? The future of space exploration is not just a scientific pursuit, it's a question of philosophy, politics, ethics, and human ambition. What happens if we discover an alien artifact drifting through space, proof of a civilization that existed long before us, or perhaps one that still exists somewhere out there? Would it unite humanity with a sense of shared purpose? Or would it spark fear and competition, as nations and corporations scramble to control access to alien knowledge? Even if these discoveries never happen in our lifetime, the search itself changes us. The more we learn, the more we are forced to ask the biggest questions of all. What is reality? If time and space can bend, stretch, and warp under the right conditions, does that mean our perception of reality is incomplete? That we are only scratching the surface of something far deeper? Could our universe be just one of many? A small pocket in a vast multiverse, where entirely different laws of physics govern realities beyond our comprehension? And if so, what does that mean for everything we think we understand about existence? Some theories suggest that consciousness itself may be connected to the fundamental nature of the universe, that the act of observation might shape reality in ways we don't yet fully grasp. Could the human mind, the very thing that allows us to wonder about these mysteries, be more powerful than we realize? Could the key to understanding the cosmos be hidden within us, just as much as it is out there among the stars? This is why the mysteries of the universe matter, not just for scientists or astronomers, but for everyone. Because they force us to confront the unknown, to challenge our assumptions, to push the boundaries of human understanding. They make us question the nature of existence itself, and remind us that, despite all our knowledge, we are still explorers standing at the edge of an infinite abyss, daring to look deeper. The next great discovery could happen at any moment. The universe has been unfolding its secrets for billions of years, waiting for us to notice. So, what do you think? Are we on the verge of a discovery that will change everything? If you had the chance to ask the universe one question and receive an answer, what would it be? Let's discuss. Because the future of cosmic exploration isn't just about what we find, it's about what we choose to seek. The universe stretches infinitely, in all directions, an endless expanse of darkness punctuated by the cold fire of distant stars. Beyond the reach of our atmosphere, past the fragile shell of Earth's thin blue sky, lies a realm so vast that even our most powerful telescopes struggle to grasp its immensity. In this place, time and space are not as we know them. Galaxies drift through the void like islands in a cosmic ocean, each one containing billions of stars, their light traveling for millions, even billions, of years before reaching us. Some of these stars burn hot and young, their nuclear furnaces forging the elements of life, while others, ancient and dim, hover at the edge of existence, awaiting the inevitable collapse into white dwarfs, neutron stars, or the bottomless gravity wells of black holes. The universe is both a graveyard and a birthplace, a place where stars die in fiery supernovae, scattering their remains across the void, only for new suns to rise from the ashes of the old. Yet for all the brilliance of starlight, most of the universe is defined by darkness. The vast intergalactic voids stretch for millions of light years, great cosmic deserts where matter is sparse and gravity's pull is weak, places where entire galaxies are separated by distances so extreme that they may never interact across the lifetime of the cosmos. Even within galaxies, the spaces between stars are unfathomably vast distances, so immense that even light, the fastest thing in the universe, can take centuries or millennia to cross them. And lurking within this darkness is a force we barely understand: dark matter, an invisible presence that outweighs all the visible stars and galaxies combined, holding them together in an unseen grip, shaping the structure of the universe itself. It neither emits nor absorbs light, yet we know it must be there because of its gravitational effects, bending the paths of galaxies, distorting the fabric of space-time in ways we can measure but cannot yet fully explain. Even stranger is dark energy, a mysterious force that seems to be driving the universe apart, accelerating its expansion at an ever-increasing rate, as if space itself is stretching, pushing the galaxies farther from one another into an uncertain future. Amidst this grand, unknowable vastness, humanity has only just begun to scratch the surface of understanding. The history of cosmology is filled with visionaries who have shaped our view of the universe, from the ancient astronomers who first charted the movement of the stars to the modern physicists unraveling the secrets of space-time. In the 16th century, Nicolaus Copernicus dared to challenge the prevailing geocentric view, placing the Sunday at the center of the solar system and setting the stage for Galileo Galilei's groundbreaking observations with the telescope. Johannes Kepler refined the motions of the planets, revealing that they move in ellipses, not perfect circles, while Isaac Newton provided the mathematical framework that explained their motion through the force of gravity. In the 20th century, Albert Einstein revolutionized physics with his theories of relativity, showing that space and time are not fixed, but malleable, bending and stretching under the influence of gravity, concepts that would later help explain the warping of light around massive cosmic objects and the behavior of black holes. Then came Edwin Hubble, whose observations in the 1920s shattered the idea that the Milky Way was the entirety of the universe. By measuring the redshift of distant galaxies, he proved that they were moving away from us, leading to the groundbreaking realization that the universe is expanding, an insight that laid the foundation for the Big Bang Theory, the idea that all of existence began as an infinitely dense point, a singularity, exploding outward in a cosmic birth that set time and space into motion. Since then, our understanding of the universe has continued to evolve at a staggering pace, with discoveries such as the cosmic microwave background radiation, the faint afterglow of the Big Bang, providing critical evidence for the universe's early state, and the detection of gravitational waves, ripples in space-time caused by the violent collisions of black holes, confirming Einstein's predictions and opening a new window into the study of the cosmos. Despite these advancements, the universe remains an enigma, a puzzle with far more missing pieces than solved ones. The event horizons of black holes mark the boundaries of the unknown, places where our understanding of physics breaks down, where the laws of time and space seem to collapse into singularity. The question of what lies beyond them, whether it is a bridge to another universe, a gateway to a deeper layer of reality, or simply a place where information is lost forever, continues to haunt theoretical physics. Then there is the mystery of the multiverse, the idea that our universe is just one of many, that beyond the cosmic horizon there may be an infinite number of parallel realities, each with its own set of physical laws, some eerily similar to ours, others utterly alien. Yet for all its strangeness, the universe is not just a distant, untouchable expanse. It is our home, the place where every atom of our being was forged in the heart of a star. It is the backdrop to our existence, the stage upon which life, in all its fleeting brilliance, unfolds. And as we continue to explore it, sending probes to the outer planets, building telescopes capable of peering into the deepest reaches of space, and one day perhaps venturing beyond our own solar system, we carry with us an unshakable sense of wonder, a deep, primal urge to seek out the unknown, to find meaning in the vastness, to look up at the night sky and know that we are part of something far greater than ourselves. As humanity peers deeper into the cosmos, chasing the limits of our observable universe, an unsettling realization begins to emerge. The more we discover, the more we are forced to question whether we will ever reach the true edge of reality. Every technological leap, every telescope launched into the void, every particle smashed in high-energy collisions seems to illuminate more questions than answers, revealing paradoxes and contradictions that suggest our understanding of the universe may forever remain incomplete. What if the cosmos is not only infinite, but fundamentally unknowable in ways we cannot yet comprehend? What if the very act of searching for an edge is misguided, a product of human perception trying to impose structure on something that may not have a boundary at all? Could it be that the universe, in its most fundamental nature, is beyond the grasp of our observational tools, our mathematical models, and even our cognitive abilities? These doubts are not merely philosophical. They are rooted in the very fabric of modern physics, in the contradictions and paradoxes that continue to challenge our best theories. One of the earliest signs that our quest for a final answer may be doomed lies in the very nature of light and time. When we observe the most distant galaxies, we are not seeing them as they are now, but as they were billions of years ago, their light having traveled across cosmic distances to reach us only now. The farther we look, the deeper into the past we peer, yet even with the most powerful telescopes, we will always face a limit, the point where light has not yet had time to reach us, the edge of our observable universe. But what lies beyond? If we could somehow travel past that horizon, would we find more galaxies stretching infinitely into the unknown? Or would we encounter something else entirely, a fundamental boundary where space itself ends, or loops back in ways we cannot yet imagine? Some physicists suggest that our universe may curve back onto itself, an endless, boundless expanse with no true edge, while others propose that it may be just one of many, a single bubble in an infinite multiverse, forever cut off from the rest. This uncertainty is further compounded by the paradoxes that have plagued physics for over a century, contradictions that hint at deep flaws in our understanding of space, time, and matter. The incompatibility of general relativity and quantum mechanics is one of the greatest unresolved conflicts in science, a battle between two theories that each accurately describe reality in their own domain, yet utterly fail to coexist. General relativity, Einstein's grand theory of gravity, describes the universe on a large scale, explaining how planets orbit stars, how galaxies bend light, and how massive objects distort space-time itself. But when we zoom in to the smallest scales, the level of atoms and subatomic particles, relativity ceases to work, and instead, we must turn to quantum mechanics, a theory that operates on probabilities, wave functions, and bizarre phenomena like entanglement, where particles seem to influence one another instantaneously, defying classical notions of cause and effect. These two pillars of physics should, in theory, merge into a single unified framework, a theory of everything. But despite decades of effort, the pieces refuse to fit. Some physicists believe that resolving this conflict may require an entirely new understanding of reality, one that forces us to abandon long-held assumptions about the nature of space, time, and even existence itself. Perhaps nowhere is this tension more evident than in the study of black holes, the cosmic enigmas that seem to defy all logic. According to general relativity, a black hole is a region of space-time where gravity becomes so extreme that nothing, not even light, can escape its grasp. But quantum mechanics predicts that black holes must emit radiation, slowly evaporating over time in a process known as Hawking radiation. This leads to the infamous information paradox. If a black hole eventually disappears, what happens to the information it once contained? Does it vanish forever, violating the fundamental laws of physics? Or is it somehow preserved in ways we do not yet understand? Some have suggested that information is stored on the event horizon, encoded in a way that hints at deeper connections between gravity and quantum mechanics, while others propose that black holes may be gateways to other universes, places where the known laws of physics break down completely. And if black holes challenge our understanding of space, then what about the Big Bang itself? If the universe began as a singularity, much like a black hole, then does that mean our entire cosmos emerged from a paradox, a place where our current theories of physics collapse into meaninglessness? Adding to this uncertainty are the observational constraints that limit what we can ever hope to see or measure. Even if the universe extends beyond the observable horizon, we may never be able to prove it, as the speed of light imposes a fundamental limit on how far information can travel. If an event occurs billions of light years beyond our reach, it may as well not exist as far as human observation is concerned. Moreover, the universe's accelerating expansion, driven by the mysterious force known as dark energy, is pushing distant galaxies away from us at speeds that will eventually surpass the speed of light itself, meaning that some regions of the cosmos will forever drift beyond our ability to study them, lost to us for all of time. This raises a haunting question. Are we trapped in a shrinking observational bubble, doomed to see less and less of the universe as time goes on, rather than more? Could there be entire structures, cosmic civilizations, vast celestial phenomena, hidden realms of physics that exist beyond our reach, forever beyond the limits of what we can detect? And yet, even as our understanding is challenged at every turn, we continue to push forward, driven by the relentless human desire to know. Each new discovery reshapes the questions we ask, forcing us to confront the limits of our knowledge while offering tantalizing glimpses of what lies beyond. Will we one day find a way to unify gravity and quantum mechanics, unlocking a deeper reality that has eluded us for centuries? Will new observational TechniQuest quantum telescopes, gravitational wave detectors, even future missions beyond our solar system allow us to pierce the veil of the unknown, revealing answers that are currently hidden in the cosmic darkness? Or will we reach a point where we must accept that some mysteries are simply beyond our grasp, that the true nature of the universe will always remain just out of reach? This, perhaps, is the greatest conflict of all, the tension between our desire for absolute knowledge and the possibility that the universe itself may be fundamentally unknowable. It is a struggle that has defined human inquiry since the dawn of civilization, a question that has driven explorers, scientists, and dreamers to push the boundaries of what is possible. And as we continue to search, to send our instruments into the void, to build new theories and test the limits of reality itself, we must ask, are we approaching the final frontier of human understanding, or have we only just begun to glimpse the true vastness of what lies beyond? The search for the true nature of the universe has led to one of the greatest intellectual battles in human history, a struggle between competing theories, incomplete observations, and the profound limits of human comprehension. At the heart of this conflict is a fundamental question: does the universe have an edge, a boundary beyond which nothing exists, or is it infinite, stretching forever in all directions? This seemingly simple question has divided cosmologists for decades, sparking fierce debate, radical hypotheses, and an ongoing clash between observable evidence and theoretical models that often refuse to align. Every breakthrough, every new discovery, adds another layer of complexity, revealing deeper paradoxes that challenge the very foundations of modern physics, forcing scientists to question whether our current understanding of the cosmos is even capable of grasping the full picture. One of the central tensions in modern cosmology is the struggle between two opposing models of the universe: the finite universe, which suggests that space has a definite size, and the infinite universe, which proposes that it extends forever without limit. The finite model is often easier to conceptualize. If the universe had a beginning, as the Big Bang Theory suggests, then it must have expanded from a single point, meaning that it should have a measurable size, even if that size is beyond our ability to see. Some physicists argue that the universe is shaped like a four-dimensional sphere, meaning that if you traveled far enough in one direction, you would eventually return to your starting point, much like walking around a planet. This idea aligns with general relativity and solves certain mathematical problems, but it raises deeper philosophical questions. If space is curved back onto itself, what exists beyond that curvature? Is there a higher dimensional structure enclosing our universe? And if space is finite, does that mean it has a boundary, an edge beyond which there is nothing? If so, what is the nature of nothingness? And can such a concept even exist? Opposing this view is the possibility that the universe is truly infinite, that space has no boundary and no end, stretching beyond our observable horizon in an unbroken expanse. This model is supported by certain solutions to Einstein's equations, which allow for an eternally expanding universe without a defined edge. If true, this would mean that not only does space extend forever, but so do its contents an infinite number of galaxies, an endless repetition of cosmic structures, and, if the laws of physics allow, even an infinite number of versions of you, existing in parallel across an unfathomable cosmic sea. The implications of an infinite universe are staggering, as they suggest that every possible event, every variation of existence has already occurred somewhere, an idea that challenges not just physics, but philosophy, identity, and the very nature of reality itself. Yet for all its appeal, the infinite universe hypothesis presents problems of its own. If the cosmos is truly without end, then why does it appear to have originated from a single event? How does an infinite universe emerge from a finite Big Bang? And if space stretches infinitely, why does it appear uniform rather than chaotic and unpredictable? Complicating this battle is the issue of observational constraints. No matter how powerful our telescopes become, we can only observe a limited portion of the universe, the region from which light has had time to reach us since the Big Bang. This observable universe is roughly 93 billion light-years across, a sphere of space containing hundreds of billions of galaxies. Yet beyond that horizon, we have no direct knowledge of what exists. Is the structure of the universe beyond our reach fundamentally different from what we see? Could it be that the laws of physics themselves change at extreme distances? Some theories propose that space beyond our observable horizon may be arranged in ways that are radically different from anything we can imagine, with alternative physical constants, exotic forms of matter, or even entire regions where time flows differently. If this is true, then any attempt to define a universal model of the cosmos may be inherently flawed, as we may never have access to the full picture. Adding to the conflict are the unresolved contradictions between general relativity and quantum mechanics, the two pillars of modern physics that refuse to be reconciled. General relativity governs the behavior of the universe on the largest scales, describing gravity as a curvature of spacetime. Yet when applied to the smallest scales, the realm of quantum particles, it breaks down completely, failing to explain the chaotic, probabilistic nature of quantum fields. Meanwhile, quantum mechanics accurately describes subatomic interactions, yet it provides no coherent explanation for gravity or the structure of spacetime. This divide is at the heart of the greatest crisis in physics, as it suggests that our current models are incomplete, that a deeper, undiscovered theory, possibly quantum gravity or string theory, must exist to unify these two domains. Until such a theory is found, our understanding of the universe remains fragmented, with black holes, dark energy, and the very nature of spacetime itself remaining unexplained. Nowhere is this conflict more evident than in the study of the cosmic beginning. The Big Bang theory, supported by overwhelming observational evidence, such as the cosmic microwave background radiation and the redshift of galaxies, tells us that the universe began as a singularity, an infinitely dense point where space and time were compressed into an incomprehensible state. But the very concept of a singularity is a mathematical failure, a point where physics ceases to function, suggesting that our current models are missing something fundamental. Some cosmologists argue that the Big Bang may not have been the true beginning, but rather a transition from a previous cosmic state, possibly a big bounce, where a collapsing universe gave birth to a new expansion. Others propose that the Big Bang itself was merely a localized event within a larger multiverse, meaning that our cosmos is just one of many, each with its own beginning, evolution, and physical laws. If this is true, then the question of the edge becomes even more complex. Does each universe have a boundary, or do they merge together in a higher dimensional reality that transcends our understanding? At the heart of these debates lies a profound tension between theory and observation, between what we can see and what we can only infer. Some of the most critical components of the universe, dark matter and dark energy, are entirely invisible to us, known only through their gravitational effects, yet they make up the vast majority of cosmic mass and energy. We have no direct proof of what they are, yet without them, our models of galaxy formation and cosmic expansion fall apart. If our current understanding relies so heavily on unseen forces, how can we be certain that our theories are correct? Could it be that our entire framework of physics is missing a deeper, hidden reality that lies just beyond our reach? Ultimately, the struggle to define the edge of the universe is not just a scientific battle, it is a philosophical one, a confrontation with the limits of human knowledge and the nature of reality itself. If the universe is infinite, we may never truly know its full extent. If it is finite, we may never reach its boundary to see what lies beyond. We are trapped in a paradox, caught between the urge to define everything and the possibility that some answers may forever remain hidden. Yet despite these challenges, the search continues, driven by the unshakable human desire to understand, to push beyond the limits of the known, to seek answers in the cosmic void. Whether we will ever find them remains uncertain, but the quest itself, the struggle between competing ideas, the clash of theories, the pursuit of truth in the face of the unknownness, what defines us as explorers of the universe. If the universe has no edge, if it stretches infinitely in all directions without boundary or limit, then the implications for physics, cosmology, and human understanding are profound, shaking the foundations of everything we assume about reality. An infinite universe challenges our deepest scientific principles, forces us to question the very nature of existence, and redefines humanity's place in the cosmos. It suggests that no matter how far we explore, no matter how advanced our technology becomes, there will always be more galaxies, more structures, more unknowns stretching beyond the limits of our perception. Such a reality alters our understanding of time, space, and causality, rendering certain fundamental assumptions obsolete while demanding new physics that transcends the constraints of our current models. For physicists, the notion of a boundless cosmos creates an immediate crisis, particularly regarding the origins of the universe. If the universe has no edge, then what was the Big Bang? Did it truly mark the beginning of everything? Or was it merely a localized event in an already infinite expanse? The standard model of cosmology suggests that the observable universe expanded from an incredibly dense, hot state. But if space itself is infinite, then the Big Bang may not have been the start of all existence, just the beginning of the region we can see. This opens the door to the idea that multiple Big Bangs could have occurred, each creating its own observable domain, separated by distances too vast to measure. In this case, our universe would not be unique, but rather one of countless cosmic regions, each following its own evolutionary path. This interpretation aligns with some versions of inflation theory, which propose that space expands eternally in a process known as eternal inflation, constantly creating new universes within an ever-growing multiverse. If true, this means that our cosmos is not a singular entity but part of a vast, self-replicating structure beyond all comprehension. Such a scenario forces us to reconsider the very laws of physics themselves. If the universe has no boundary, then it is possible that different regions of space obey different physical laws. Some parts of the cosmos might contain familiar elements and forces, while others might operate under entirely alien principles, governed by different constants or even entirely different dimensions of reality. This suggests that the fundamental laws of physics we rely on may not be universal, but instead emergent properties of our particular cosmic region. Gravity, electromagnetism, and the nuclear forces that shape our reality may not be absolute truths, but rather local phenomena specific to the conditions of our observable universe. This presents a profound challenge to theoretical physics, which seeks to uncover a theory of everything that applies to all of existence. If different regions of the universe follow different rules, then no single equation may be capable of describing all of reality. Instead, we may need to embrace a more flexible framework, one that acknowledges variability in fundamental forces across different domains of space. The consequences of an infinite universe extend far beyond physics into philosophy and human identity. If space is boundless, then everything that can happen must happen somewhere, an idea with staggering implications. In an infinite cosmos, the number of possible arrangements of matter is also infinite, which means that somewhere out there, every conceivable variation of reality must exist. This includes exact copies of our own planet, our own solar system, and even our own lives. Somewhere, in the vast stretches of space, there could be another version of you, living a nearly identical life, with only the smallest variations. And if the universe is truly infinite, then there must be not just one, but an infinite number of versions of you, each experiencing a different fate, making different choices, living out different possibilities. This challenges our very sense of self. What does it mean to be unique if an infinite number of copies of you exist elsewhere? Does free will have any meaning in a universe where every possible outcome has already played out somewhere else? Beyond identity, an infinite universe reshapes our understanding of purpose and meaning. Traditional cosmology gives us a narrativa beginning with the Big Bang, a cosmic evolution leading to the formation of galaxies, stars, planets, and life, culminating in the present moment. But if the universe has no edge, no boundary, no true beginning or end, then what is its purpose? Is there a grand design? Or is existence simply an unending, self-replicating process without ultimate meaning? If the universe has no limit, then perhaps it has no final destiny, no single answer to the question of why. Instead, meaning may be something we impose upon it, a construct of human thought, rather than a fundamental property of reality. This existential dilemma raises another unsettling question. How does humanity fit into an infinite cosmos? In a finite universe, the emergence of life, intelligence, and civilization can be seen as rare and precious, a unique phenomenon shaped by a chain of specific cosmic events. But in an infinite universe, life must also be infinite, existing in every possible form, from simple microbes to hyper-advanced civilizations beyond our imagination. This raises the Fermi paradox to a new level of intelligent life. Is inevitable in an infinite cosmos, then why do we not see it? Where are the civilizations that should have already spread across the stars? One possibility is that in an infinite universe, intelligent life is so widely scattered that the distances between civilizations are simply too great for meaningful contact. Another is that the conditions necessary for advanced intelligence are far rarer than we assume, making life a fleeting anomaly in a vast sea of sterile galaxies. Or perhaps civilizations do exist, but remain hidden, either by choice or by necessity, locked within their own cosmic regions, separated by impassable distances or unknown physical barriers. The implications of an infinite universe also extend into the need for new physics, as our current models struggle to accommodate such vastness. The very fabric of space-time may be more complex than we realize, with hidden dimensions or topological structures that prevent us from directly perceiving the true scale of reality. Some theories suggest that the observable universe is only a projection of a higher dimensional space, much like a three-dimensional shadow cast by a four-dimensional object. If this is true, then our attempts to define an edge may be meaningless, as what we perceive as boundaries could be illusions created by our limited perspective. This ties into the idea of the holographic principle, which suggests that all the information in our universe may be encoded on a distant cosmic boundary, a concept that radically redefines space and reality itself. Yet, despite these profound implications, the search for the structure of the universe continues. Cosmologists push the limits of observation, seeking new ways to probe the cosmic horizon, hoping to detect signs of curvature, patterns in the cosmic microwave background, or anomalies that might hint at a larger framework beyond what we can see. Quantum physicists work to unify gravity and quantum mechanics, seeking a deeper theory that might resolve the contradictions that currently divide our understanding. And philosophers and thinkers wrestle with the existential consequences, trying to reconcile human meaning with a universe that may have no ultimate boundary. Whether the universe is infinite or finite, the conflict it presents is a defining challenge of our time. It forces us to confront not just the nature of space and time, but the nature of existence itself. If there is no edge, then what we seek may not be a final answer, but an ever-expanding horizon of understanding, a journey with no ultimate destination, only deeper and deeper layers of discovery. And perhaps that, in itself, is the answer, that the universe is not meant to be fully known, that its greatest truth is its infinite capacity to inspire wonder, to challenge our minds, and to push us ever forward into the unknown. The pursuit of understanding the universe has been a journey filled with both triumph and frustration, a constant battle between human curiosity and the vast, unknowable depths of the cosmos. But every so often, a discovery emerges that shifts the entire trajectory of science, forcing us to reevaluate what we thought we knew and propelling us into new realms of understanding. These turning point scientific revelations that reshape the very foundation of physics and cosmology led to some of the most profound breakthroughs in human history. From the realization that our universe is expanding to the enigmatic force of dark energy accelerating this expansion, and the powerful technologies that allow us to peer into the deepest corners of the cosmos, each discovery has pushed us closer to answering the greatest question of all. What is the true nature of our universe? One of the most significant revelations in modern cosmology came with the discovery that the universe is not only expanding, but that this expansion is accelerating. This breakthrough shattered our previous understanding of cosmic evolution, forcing scientists to reconsider the long-term fate of the universe. The story begins in the early 20th century with Edwin Hubble, whose observations of distant galaxies in the 1920s provided the first evidence that space itself was expanding. By measuring the redshift of light from galaxies show their wavelength stretched as they moved away, Hubble demonstrated that the farther away a galaxy was, the faster it was receding. This was a groundbreaking moment, confirming that the universe had a dynamic history and likely originated from a single dense point in the past, what would later be called the Big Bang. For decades, physicists believed that the universe's expansion would eventually slow due to the gravitational pull of all its matter. The key question was whether the cosmos contained enough mass to eventually reverse this expansion, leading to a big crunch where everything would collapse back into a singularity, or if it would continue expanding indefinitely at a steady rate. But in 1998, two independent teams of astrophysicists, Supernova Cosmology Project and the High Z Supernova Search Team, made a shocking discovery. By studying distant type Ia supernovae, which serve as cosmic mileposts due to their predictable brightness, they found that these explosions were dimmer than expected, indicating that they were farther away than they should be if the universe's expansion were slowing. Instead, something was driving the universe apart at an ever-increasing rate. This mysterious force, now known as dark energy, is one of the most perplexing discoveries in modern physics. Unlike dark matter, which interacts with gravity but remains invisible, dark energy seems to work against gravity, repelling rather than attracting, causing space itself to stretch. What exactly is dark energy? No one knows for certain. Some theorists suggest it could be a property of space itself, a built-in energy that exists even in the vacuum of nothingness, an idea that aligns with Einstein's concept of a cosmological constant, an invisible force he once inserted into his equations to allow for a static universe, later dismissing it as his greatest mistake. Others speculate that dark energy could be the result of an undiscovered quantum field, a force that emerges from fluctuations in empty space, or even a sign that our understanding of gravity is incomplete, requiring new physics beyond Einstein's general relativity. The implications of dark energy are staggering. If this repulsive force continues to dominate, the universe's ultimate fate may not be a gentle stretching into infinity, but something far more dramatic. Some theories suggest a big rip, where dark energy's expansion accelerates to the point that galaxies, stars, planets, and eventually atoms themselves are torn apart as space expands faster than light can travel. Others propose that dark energy might evolve over time, potentially reversing its effect or even collapsing the universe into a new state of existence. Whatever the outcome, dark energy represents a fundamental unknown, a force that challenges everything we thought we understood about the cosmos. As dark energy reshapes our understanding of the universe's destiny, another technological revolution has been unfolding, one that has allowed us to see deeper into space than ever before. The launch of the Hubble Space Telescope in 1990 marked a turning point in observational astronomy, providing humanity with crystal-clear images of the universe free from the distortions of Earth's atmosphere. Hubble's deep-field images, taken by staring at what appeared to be empty patches of sky, revealed thousands of previously unseen galaxies stretching back billions of years, offering an unprecedented view of cosmic history. These images not only confirmed the vastness of the universe, but also provided crucial data about galaxy formation, black holes, and the distribution of dark matter. But Hubble was just the beginning. In 2021, the James Webb Space Telescope, JWST, launched, ushering in a new era of discovery. Unlike Hubble, which primarily observed visible and ultraviolet light, Webb operates in the infrared spectrum, allowing it to peer through dust clouds that obscure distant galaxies and detect the faintest, most ancient light from the first stars and galaxies formed after the Big Bang. Within months of operation, Webb had already provided astonishing insights, revealing distant galaxies that appear more massive and developed than expected, challenging existing models of cosmic evolution. Some of its observations hint at the possibility that our understanding of the early universe may need revision, that the formation of galaxies, black holes, and large-scale structures occurred faster than previously thought. Beyond distant galaxies, Webb is also revolutionizing the study of exoplanets, worlds beyond our solar system. By analyzing the atmospheres of planets orbiting other stars, Webb can detect potential signs of habitability, even searching for biosignature chemical markers that might indicate the presence of life. This has profound implications for the search for extraterrestrial intelligence. If Webb or future telescopes were to detect evidence of life, even microbial, on another world, it would fundamentally alter our understanding of biology, evolution, and our place in the cosmos. And if intelligent civilizations exist elsewhere, the discovery could force us to confront new philosophical and existential dilemmas. Are we truly unique, or is life a common occurrence in the vastness of space? Meanwhile, advances in gravitational wave astronomy are opening an entirely new window into the universe. First detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, gravitational waves are ripples in space-time, caused by violent cosmic events such as black hole mergers and neutron-star collisions. These waves allow us to study the universe in a way that was previously impossible by detecting signals from events that do not emit light, but instead distort the very fabric of reality itself. Future observatories, such as the planned Laser Interferometer Space Antenna, LISA, will be able to detect even more subtle gravitational waves, potentially revealing new insights into dark matter, cosmic inflation, and the structure of space-time. As each new technology pushes the boundaries of observation, our understanding of the universe continues to evolve at an accelerating pace. But every breakthrough also raises new questions, forcing us to grapple with the limits of human knowledge. Dark energy remains an unsolved mystery. Quantum gravity remains elusive, and the ultimate fate of the cosmos remains unknown. Yet, in this uncertainty lies the greatest adventure of all, the pursuit of answers, the challenge of confronting the unknown, and the realization that no matter how much we discover, there will always be more to explore. The turning point in our understanding of the universe is not a single event, but an ongoing revolution, a relentless expansion of knowledge that drives humanity ever forward. The mysteries of dark energy, the discoveries of space telescopes, and the emergence of gravitational wave astronomy are not just scientific milestones. They are stepping stones to an even deeper understanding of existence itself. As we continue to push the limits of what is possible, we may one day find the answers we seek, or perhaps, as history has shown time and again, each discovery will only open the door to even greater mysteries waiting to be uncovered. For centuries, humanity has approached the universe with the assumption that it is a vast, three-dimensional expanse filled with galaxies, stars, and planets, all governed by the familiar laws of physics. We have sought to define its boundaries, its shape, its origin, and its fate. But what if we have been asking the wrong questions? What if our fundamental perception of the cosmos is flawed, an illusion born from our limited ability to observe and measure reality? Some of the most radical theories in modern physics suggest that our understanding of space, time, and even existence itself may need to be completely reimagined, forcing us to shift our perspective in ways that challenge not only scientific convention, but also the very nature of human thought. One of the most revolutionary ideas in contemporary physics is the holographic principle, a concept that suggests that the three-dimensional universe we experience may actually be a projection of information encoded on a two-dimensional surface. This theory emerges from the study of black holes, where it has been found that all the information about a black hole's interior can be described by fluctuations on its outer surface, known as the event horizon. If this principle applies to black holes, some physicists have speculated that it might extend to the entire universe, implying that our reality itself is a kind of hologram, with everything we perceive as solid and real being just a higher dimensional projection of fundamental quantum information encoded on a distant cosmic boundary. If the holographic principle is correct, it would fundamentally alter our understanding of space and time. It would mean that the fabric of the universe is not as continuous as it seems, but rather emerges from an underlying structure governed by quantum mechanics. Space would not be an empty void, but a construct generated from the interplay of quantum information. Time itself might be an emergent property rather than a fundamental dimension, a concept that challenges our most basic assumptions about cause and effect. Such a perspective forces us to reconsider the concept of an edge to the universe. If space is a projection, then its perceived limits may be nothing more than artifacts of the way information is organized, rather than physical boundaries in any conventional sense. This shift in perspective has profound implications for our understanding of cosmic structure. Traditional physics describes the universe in terms of fundamental particles, forces, and fields interacting within spacetime. However, quantum mechanics suggests that at its deepest level, reality is not made up of things, but rather probabilities, wave functions, and entangled states. The conflict between general relativity, which describes gravity on a large scale, and quantum mechanics, which governs the smallest scales of reality, has long been one of the greatest challenges in physics. If space and time are emergent properties rather than fundamental ones, this could provide a pathway toward resolving this tension, as gravity itself might arise from quantum entanglement rather than being a separate force. One of the strongest indicators that we may need to rethink our perception of reality comes from the study of quantum entanglement. When two particles become entangled, their properties remain linked regardless of distance, meaning that measuring one instantly determines the state of the other, even if they are separated by billions of light years. This phenomenon, famously described by Einstein as spooky action at a distance, suggests that information can be transmitted instantaneously across vast distances, seemingly violating the constraints of relativity. But rather than viewing this as a paradox, some physicists believe it may hint at a deeper structure underlying the universe, one where spacetime itself is a network of entangled quantum states rather than a smooth, continuous expanse. If this is true, then distance, as we perceive it, may be an illusion. Separate points in space could actually be directly connected at a fundamental level, meaning that the true nature of cosmic structure is far more intricate than we currently realize. Another alternative theory that challenges conventional thinking is loop quantum gravity, which proposes that space is not infinitely divisible, but instead consists of discrete chunks or quantized units. In this model, spacetime is not a smooth continuum, but a vast, interwoven network of microscopic loops, much like a woven fabric. If true, this would mean that the notion of an edge to the universe might not even be meaningful. Rather than having a boundary, space might simply dissolve into an entirely different quantum reality at its most fundamental level. This would also help resolve some of the paradoxes of black holes, as the traditional concept of a singularity, a point of infinite density, might instead be replaced by a region where spacetime itself ceases to exist in any conventional sense. These radical shifts in perspective are not just theoretical exercises. They actively reshape scientific discussions and influence the direction of modern research. By questioning the very foundations of our understanding, physicists are forced to develop new models, design new experiments, and reconsider long-held assumptions. For instance, the search for quantum gravity, which aims to unify Einstein's relativity with quantum mechanics, is no longer limited to mathematical speculation. It is now being tested through high-energy particle experiments, black hole observations, and even astrophysical studies of cosmic microwave background radiation, which may contain hidden clues about the true nature of spacetime. Moreover, these ideas have profound implications for the concept of the multiverse, the hypothesis that our universe is just one of many, each with its own set of physical laws and constants. If space itself is a quantum construct, then it is possible that what we perceive as our universe is just a small region within a much larger quantum landscape, a bubble of ordered reality floating within an infinite quantum field. In this case, the idea of an edge to the universe would be irrelevant to our cosmos, may simply be one of countless others, with different physical rules and even different forms of intelligence, existing beyond the limits of our observation. A shift in perspective also influences how we interpret data from space telescopes and other observatories. Traditionally, cosmologists have assumed that the structures we observe, galaxies, galaxy clusters, dark matter distributions, are physical entities that evolved according to predictable laws. But if space itself is an emergent property, then what we see might be only one layer of a deeper reality. Could there be hidden dimensions curled up within the fabric of space-time, as string theory suggests? Could dark matter and dark energy be manifestations of unknown quantum interactions rather than separate physical substances? The ability to frame these questions differently allows scientists to approach them from new angles, leading to breakthroughs that would not have been possible under traditional assumptions. As we continue to explore the cosmos, the role of quantum mechanics in shaping our understanding of the universe becomes more apparent. The mysteries of dark energy, the expansion of space, and the behavior of black holes all suggest that there is a deeper order to reality that remains hidden beneath the surface of our observations. Whether through the holographic principle, loop quantum gravity, or other emerging theories, we are beginning to realize that space, time, and even matter itself may not be what they seem. This realization does not diminish the wonder of the universe, it enhances it, revealing that the truth is far stranger, far more beautiful, and far more intricate than we ever imagined. Ultimately, the greatest breakthroughs in science often come not from finding new answers, but from asking better questions. If we have been looking at the universe the wrong way, then the future of cosmology lies not in refining old models, but in completely rethinking what we mean by space, time, and existence. Perhaps the edge of the universe is not a physical boundary, but a conceptual one, the limit of our current understanding, waiting to be transcended. And as we push beyond that limit, we may find that the universe is not only more complex than we think, but more complex than we can think, a reality so vast, so intricate, and so interconnected that our current perspectives are only the first step towards something far greater. The greatest discoveries in science often emerge not as confirmations of what we expect, but as challenges to everything we assume to be true. Throughout history, humanity has repeatedly believed it stood at the precipice of total understanding, only for the universe to reveal something so unexpected, so fundamentally disruptive, that it forces a complete reevaluation of reality itself. As we continue to probe the cosmos, we now find ourselves at yet another such turning point, where some of the most groundbreaking discoveries of modern physics are beginning to suggest that the nature of the universe and our place within it may be far stranger than we ever imagined. One of the most shocking revelations in recent decades is the possible existence of a multiverse, the idea that our universe is just one of countless others, each with its own physical laws, constants, and possibly even alternate versions of history. For most of scientific history, cosmology has been based on the assumption that the universe is a single, self-contained system governed by universal laws. But now, emerging theories in quantum mechanics, inflationary cosmology, and string theory have begun to suggest that the reality we perceive may be just a small slice of an unimaginably vast structure. If true, this would mean that everything we know, the stars, the galaxies, the fundamental laws of physics may be unique only to our particular pocket of existence, while completely different universes exist beyond our reach, where alternate versions of reality unfold with entirely different rules. One of the strongest pieces of evidence for the multiverse comes from cosmic inflation theory, which describes the rapid expansion of space in the earliest moments after the Big Bang. According to inflation, the universe expanded exponentially in a fraction of a second, smoothing out irregularities and creating the large-scale structure we observe today. However, certain versions of this theory suggest that while our observable universe emerged from inflation, other regions of space may have continued expanding indefinitely, spawning an infinite number of bubble universes that evolve independently from one another. Each of these universes could have its own unique laws of physics, different particle arrangements, and even different fundamental forces. Some could be entirely lifeless, while others might contain civilizations far more advanced than ours. If this is true, then the edge of our universe is not a physical boundary, but merely the limit of our ability to observe a bubble among countless others in a vast cosmic sea. As if the multiverse weren't strange enough, some physicists have begun to entertain an even more radical idea: that the universe itself might not be real in the way we traditionally think of it. The simulation hypothesis, popularized by philosopher Nick Bostrom and supported by certain interpretations of quantum mechanics, suggests that our reality might be nothing more than a highly advanced computational construct, an artificial simulation designed by an unknown intelligence. This idea is not merely science fiction. It is rooted in genuine scientific and philosophical inquiry. Proponents argue that if civilizations ever reach the capability to create detailed, simulated universes, including conscious beings who do not realize they are simulated, then statistically, it is far more likely that we are living in such a simulation rather than in the original physical reality. One of the most intriguing aspects of this hypothesis is that it provides an explanation for certain anomalies in physics, such as the fine-tuning problem, the fact that the fundamental constants of the universe seem perfectly adjusted to allow for the existence of life. If we are in a simulation, then these constants might have been programmed to produce a stable and habitable environment. Furthermore, quantum mechanics itself exhibits behavior that seems oddly suggestive of computational processes, such as wave function collapse, in which a particle only takes on a definite state when observed, similar to how information in a video game is only rendered when it is being processed by a computer. Could the strange probabilistic nature of quantum mechanics be a sign that we are witnessing the limitations of an underlying computational system? Even if the simulation hypothesis is incorrect, alternative cosmologies continue to suggest that reality is not what we once thought. Some physicists propose that our universe could be a higher dimensional structure, a brain, floating in a higher dimensional space. According to M-theory, an extension of string theory, our three-dimensional universe may be embedded in a larger multidimensional framework where multiple parallel realities coexist. If this is true, then what we perceive as the cosmos is only a limited view of a much richer and more complex structure, one where time and space behave in ways we cannot yet comprehend. Perhaps the most unsettling realization of all is that, no matter which of these theories turns out to be true, they all point to the same fundamental conclusion: we are not the center of reality. Whether we live in an infinite multiverse, a computational simulation, or a higher dimensional space, our assumptions about existence must be re-examined. This has profound implications for philosophy, consciousness, and even our understanding of meaning itself. If the universe is just one of many, then is there such a thing as an absolute truth? Or are all perceptions of reality subjective and context-dependent? If we are simulated beings, then what is the purpose of our existence here? We the products of an experiment, entertainment, or something else entirely? If our universe is part of a larger multidimensional structure, then what new laws of physics remain undiscovered? And how might they reshape our understanding of life, death, and the nature of time? What is perhaps most astonishing is that we are only at the beginning of this exploration. Our telescopes, our quantum experiments, our deep space observations, all of these are merely early steps toward uncovering a reality that may be far stranger than we ever imagined. In the coming decades, new discoveries in quantum computing, artificial intelligence, and space exploration may push us closer to answers that seem impossible today. If we do one day confirm the existence of the multiverse, or prove that reality has an underlying computational structure, it will mark not just a scientific revolution, but a transformation of human thought itself, forcing us to accept a universe that is far larger, more complex, and more enigmatic than we ever dreamed. And yet, perhaps the most profound realization is this: despite all these possibilities, our experience of the universe remains deeply personal. Whether real or simulated, finite or infinite, deterministic or probabilistic, the cosmos is still the place where we live, love, explore, and dream. Even if we are just a flicker in a vast, unknowable reality, we are still here thinking, questioning, searching. Perhaps that, more than anything, is the ultimate mystery. Why do we long to understand the universe at all? Why does existence, in whatever form it may take, strive for self-awareness? In the end, the greatest twist of all may not be that the universe is different from what we imagined, but that we have the capacity to imagine it at all. As humanity stands on the precipice of a new era in cosmology and astrophysics, we are confronted with daunting challenges that threaten to slow or even halt our progress in understanding the true nature of the universe. While groundbreaking discoveries over the past century have reshaped our perception of space, time, and reality itself, many of the biggest questions remain unanswered. The cosmos continues to defy our expectations, presenting mysteries that demand not only new theories, but also new ways of observing and exploring the universe. As we push further into the unknown, we must confront the limitations of our current technology, the logistical and financial barriers to future space missions, and the philosophical and theoretical challenges that stand in the way of a complete understanding of existence. One of the most significant obstacles we face is the fundamental limit of our observational reach. While telescopes like Hubble and the James Webb Space Telescope (JWST) have given us unprecedented views of deep space, they are still restricted by the simple fact that light takes time to travel. The farther we look into space, the further back in time we see, but we are ultimately constrained by the age of the universe itself. We can never observe anything older than 13.8 billion years, the approximate time since the Big Bang. This means that we are effectively blind to whatever came before, if anything did. The cosmic microwave background, CMB, the afterglow of the Big Bang, is the oldest light we can detect. But beyond that, we run into a wall, the so-called cosmic dark ages, a period before the first stars and galaxies formed, where no visible light was emitted at all. Understanding this early hidden history requires new observational strategies, ones that go beyond traditional telescopes and optical imaging. One way scientists hope to bypass this limitation is through the use of gravitational wave astronomy, a field that has only recently begun to yield results. Unlike light, which can be blocked or absorbed by cosmic dust and gas, gravitational wave ripples in space-time caused by massive cosmic events travel unobstructed through the universe, potentially allowing us to detect signals from the earliest moments of the cosmos. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have already revolutionized our understanding of black hole mergers and neutron star collisions, but their sensitivity is still limited. The proposed Laser Interferometer Space Antenna, LISA, a next-generation gravitational wave detector set to launch in the 2030s, will be able to detect waves from supermassive black hole mergers and potentially even primordial gravitational waves from the Big Bang itself, opening an entirely new window into the origins of the universe. Yet even with these advancements, we are still unable to answer one of the biggest questions in physics: what is dark matter? Current observations suggest that dark matter makes up approximately 85% of the universe's mass, yet it has never been directly detected. It does not emit, absorb, or reflect light, and its presence is known only through its gravitational effects on galaxies and cosmic structure. For decades, physicists have speculated that dark matter is composed of unknown subatomic particles, possibly weakly interacting massive particles, WIMPs, or axions. But so far, every attempt to directly detect these candidates has failed. Future experiments, such as the Xenont and Lux-Zeppelin detectors, are designed to be even more sensitive to potential dark matter interactions. But if they fail to find anything, we may have to rethink the very nature of gravity itself. Some physicists propose that dark matter may not be a new form of matter at all, but rather a sign that Einstein's theory of gravity is incomplete, requiring modifications at cosmic scales, an idea that remains deeply controversial. Similarly, the even greater mystery of dark energy looms over modern cosmology. This unseen force, responsible for the accelerated expansion of the universe, defies all known physics. Current models suggest that dark energy comprises roughly 68% of the universe's total energy, yet we have no concrete understanding of what it actually is. Is it a fundamental property of space itself, as Einstein's cosmological constant suggests? Is it a new exotic quantum field that pervades the cosmos? Or could it be a sign that our entire framework of physics is flawed? Addressing this question will require next-generation observatories, such as the Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, which will map the large-scale structure of the universe in unprecedented detail, helping us better understand how dark energy behaves over cosmic time. While telescopes and observatories on Earth and in orbit continue to push the boundaries of our knowledge, there is only so much we can learn from passive observation. The future of cosmology and astrophysics may require humanity to venture further into space itself. The limitations of ground-based and orbital telescopes make it clear that direct exploration may eventually be necessary to answer certain fundamental questions. For example, while we have detected exoplanets in distant solar systems, we have no way of directly studying their atmospheres or searching for microbial life beyond our solar system. Future missions, such as interstellar probes equipped with advanced propulsion systems, could allow us to physically explore nearby exoplanets, testing for signs of habitability and even life. Concepts such as Breakthrough Starshot, which proposes using powerful laser-driven sails to send probes to the Alpha Centauri system within a few decades, represent humanity's first serious attempt at interstellar exploration. Another critical challenge lies in the study of black holes and quantum gravity. One of the greatest unresolved conflicts in physics is the incompatibility between Einstein's theory of general relativity and quantum mechanics. While relativity explains gravity on a cosmic scale, quantum mechanics governs the subatomic world. And so far, the two theories do not fit together. The key to resolving this tension may lie in studying the extreme environments of black holes, where gravity is so strong that it distorts spacetime itself. The Event Horizon Telescope, EHT, which captured the first-ever image of a black hole in 2019, is only the beginning. Future space-based telescopes may be able to probe the event horizons of black holes with much higher resolution, potentially revealing new physics that could help unify gravity and quantum mechanics. Additionally, understanding the true nature of time remains one of the greatest challenges in theoretical physics. While we experience time as a continuous forward-moving phenomenon, some theories suggest that time is an emergent property, not a fundamental one. In certain interpretations of quantum mechanics, all possible states of the universe exist simultaneously, with time simply being an illusion created by the way we perceive change. Future experiments in quantum computing and entanglement studies may provide deeper insight into whether time itself is a fundamental component of reality or merely a human construct. Beyond scientific and technological limitations, there is also the practical challenge of funding and global collaboration. The kinds of projects needed to answer these grand questions, whether it be building the next generation of space telescopes, constructing massive particle colliders, or launching interstellar missions, require enormous financial investment and coordination across multiple countries. As geopolitical tensions fluctuate, the future of large-scale scientific collaboration remains uncertain. The International Space Station, ISS, and projects like the Square Kilometre Array, SKA, telescope have shown that such collaborations are possible, but long-term projects, such as building a permanent base on the Moon or sending humans to Mars, may require new models of funding and governance. Despite these challenges, the spirit of exploration continues to drive humanity forward. Each new discovery, each unanswered question, fuels the relentless pursuit of knowledge. Whether through more advanced telescopes, deeper quantum experiments, or the eventual colonization of other worlds, the quest to understand the universe will not end with the hurdles we currently face. It will only push us to invent new ways to overcome them. The universe remains a mystery, vast and indifferent, but our ability to ask questions, to build tools, and to venture into the unknown ensures that the greatest discoveries are yet to come. As humanity stands on the precipice of its greatest intellectual battle, the quest to understand the true nature of the universe, scientific community remains locked in an ongoing confrontation between competing theories, each seeking to define the fundamental fabric of reality. The mysteries of dark matter, dark energy, quantum gravity, and cosmic boundaries remain unsolved, driving physicists, astronomers, and cosmologists toward increasingly radical explanations that challenge long-standing assumptions about space, time, and existence itself. The stakes are higher than ever. If we can resolve these debates, we may unlock the deepest truths of the cosmos. If we cannot, we may be forced to accept that some answers will remain forever beyond our grasp. One of the most contentious debates in modern cosmology is the question of whether the universe has a true boundary or if it is infinite. The inflationary model of cosmology, which suggests that the universe underwent a rapid exponential expansion in its earliest moments, implies that space could stretch infinitely beyond our observable horizon. According to this view, what we see, galaxies, cosmic filaments, and vast empty voids, just a small fraction of a much larger reality, one that extends indefinitely in all directions. Some versions of inflation theory even propose that new regions of space are still being created in a process known as eternal inflation, where quantum fluctuations cause different parts of the universe to expand at different rates, leading to an infinite patchwork of cosmic domains, each potentially with its own physical laws. Yet, despite its explanatory power, the infinite universe model remains deeply unsettling to many physicists. If the universe is truly infinite, then it contains an infinite number of copies of everything, every galaxy, every civilization, every individual human being, with only the smallest variations separating them. This raises profound questions about identity, determinism, and even free will. More practically, an infinite universe makes it impossible to define total energy, entropy, or even the laws of physics as truly universal, since different regions could follow entirely different rules. This has led some physicists to search for alternative explanations, including the possibility that the universe is finite but curved, much like the surface of a sphere, meaning that while it has no physical edge, traveling far enough in one direction could eventually bring you back to your starting point. Adding further complexity is the holographic principle, a radical proposal that suggests our perception of three-dimensional space may be an illusion, with all of reality being encoded on a distant two-dimensional surface. This idea originates from studies of black holes, which suggest that all the information contained within a black hole is actually stored on its event horizon rather than inside it. If this principle applies to the universe as a whole, then what we experience as vast cosmic distances may be nothing more than a projection, with the true nature of the universe existing on a fundamentally different plane of reality. If correct, this theory could explain why gravity appears so weak compared to other fundamental forces, because gravity itself may not be a true force, but rather an emergent effect of deeper quantum interactions. The biggest battleground in this confrontation, however, remains the struggle to unify Einstein's theory of general relativity with quantum mechanics. These two pillars of modern physics describe reality on vastly different scales. Relativity governs the large-scale structure of the cosmos, explaining how planets, stars, and galaxies interact under the influence of gravity, while quantum mechanics governs the subatomic world, describing the behavior of particles, wave functions, and probabilities. Yet, when these two frameworks are brought together, such as in the intense gravitational fields of black holes, or the singularity at the Big Bang, they produce mathematical contradictions, infinities, and nonsensical results. One of the leading attempts to bridge this gap is string theory, which posits that all fundamental particles are not point-like entities, but rather tiny, vibrating strings that exist in higher dimensional space. According to string theory, space-time itself may have additional unseen dimensions, which could help explain why gravity is so much weaker than other forces. However, despite its elegance, string theory remains largely unproven, as it relies on mathematical structures that cannot yet be tested with current technology. A competing approach is loop quantum gravity, LQG, which suggests that space-time itself is not a smooth continuous fabric but is instead made up of discrete, quantized units like a cosmic grid at the smallest scales. This theory attempts to describe gravity using the same quantum principles that govern other forces, potentially resolving the contradictions between relativity and quantum mechanics. LQG also predicts that black hole singularities do not truly exist, and instead, space-time undergoes a fundamental transformation at extreme densities, possibly even leading to a big bounce, where the universe did not begin with a singularity, but instead emerged from a prior collapsing phase. Meanwhile, new discoveries continue to challenge the foundations of modern physics. Recent observations from the James Webb Space Telescope, JWST, have revealed galaxies that appear far more massive and structured than current models predicted should exist in the early universe, raising questions about whether our understanding of cosmic evolution needs revision. Similarly, experiments in quantum mechanics, such as studies of quantum entanglement, suggest that space itself may be an emergent property rather than a fundamental aspect of reality. If space-time is not truly real in the way we assume, then what does that mean for our search for a cosmic boundary? Is the question itself even meaningful? The future of cosmology will depend on whether we can push past our current technological and theoretical limitations. Upcoming space missions, such as NASA's Nancy Grace Roman Space Telescope and the European Space Agency's LISA gravitational wave detector, will allow us to study the universe with unprecedented precision, potentially revealing new physics in the distribution of galaxies and the nature of black holes. Meanwhile, next-generation particle accelerators, such as the proposed Future Circular Collider, FCC, could provide insights into whether dark matter is truly a new particle or if gravity itself needs to be redefined. Yet, for all our progress, the final question remains: will we ever truly know the full structure of the universe? If there is an ultimate boundary, whether physical, informational, or conceptual, will we be able to reach it? Or will we find, as some theorists suggest, that the act of observing itself alters reality, meaning that some aspects of the universe will always remain beyond our reach? Perhaps the answer lies not in the cosmos itself, but in how we think about it. Throughout history, every major breakthrough in physics has come not just from better technology, but from a fundamental shift in perspective. Newton's gravity replaced Aristotle's view of motion. Einstein's relativity replaced Newton's absolute space. Quantum mechanics replaced determinism with probability. Now, we stand at the edge of yet another shift tone that may force us to rethink space, time, and even consciousness itself. The final confrontation in physics is not just between competing theories, it is between our assumptions and the deeper reality that awaits beyond them. Whether we are approaching the ultimate truth or just another layer of a far grander puzzle remains to be seen. But if history has taught us anything, it is that the universe will always find a way to surprise us. The universe, vast and uncharted, has always stood as a mirror to humanity's most fundamental questions. Who are we? Why do we exist? What is the nature of reality? From the earliest days of civilization, when ancient astronomers mapped the stars with primitive tools, to the modern era of deep space telescopes and quantum physics, our quest to understand the cosmos has been more than just an intellectual pursuit. It has been a defining feature of what it means to be human. Exploring the unknown is not just about acquiring knowledge. It is about the relentless drive to push beyond our limitations, to confront the mysteries that lie at the very edge of comprehension. At its core, this journey is a testament to curiosity, the force that has propelled humanity forward since the dawn of time. It is curiosity that led us to develop fire, to craft tools, to cross oceans, and eventually, to look up at the night sky and wonder if we are alone. It is the same force that drives a child to ask why, and a scientist to devote a lifetime to solving a single equation. And while curiosity has brought us closer to the truth, it has also forced us to recognize the limits of our own understanding. With every question we answer, new ones arise. The more we know, the more we realize how much remains unknown. This balance between knowledge and mystery is what makes scientific exploration so compelling. It is a never-ending quest, one where the pursuit itself is just as valuable as the destination. One of the greatest lessons that cosmic exploration has taught us is humility. When Copernicus and Galileo first proposed that the Earth was not the center of the universe, it shattered the prevailing worldview, forcing humanity to accept that we are not the focal point of creation, but rather a small part of a much larger, indifferent cosmos. Over the centuries, this realization has only deepened. The discovery that our Sunday is just one of billions of stars in the Milky Way, that our galaxy is just one of trillions in the observable universe, and that even our known universe may be one among countless others in the multiverse, has fundamentally altered our perception of our significance. And yet, Despite our cosmic insignificance, we continue to ask, to seek, to explore, suggesting that meaning is not something given to us by the universe, but something we create through our own curiosity, imagination, and perseverance. The moral takeaway from our quest to understand the cosmos is not just about the pursuit of knowledge, but about the responsibility that comes with it. Scientific discovery is a double-edged sword. While it can illuminate the darkest corners of the unknown, it can also be misused, leading to destruction and ethical dilemmas. The same scientific progress that allowed us to map the stars also gave us the power to split the atom. The same drive that could one day take us to distant planets could also lead to unchecked technological advancements that outpace our moral development. As we stand on the brink of new frontiers, quantum computing, artificial intelligence, and interstellar travel, we must ask ourselves, how do we ensure that our pursuit of knowledge does not come at the expense of wisdom? Cosmic exploration teaches us another essential lesson: cooperation. The universe is too vast, its mysteries too great, for any one individual, nation, or generation to solve alone. The most significant scientific advancements, whether it be landing on the moon, detecting gravitational waves, or mapping the cosmic microwave background, have only been possible through collaboration across cultures, disciplines, and ideologies. This serves as a reminder that despite our differences, humanity is united by a common thread: the desire to understand. In a world often divided by borders, politics, and conflicts, the universe offers a perspective that transcends these temporary concerns, reminding us that we are all passengers on a tiny, fragile planet orbiting an ordinary star in an unremarkable corner of an incomprehensibly vast expanse. And yet, even as we explore farther into space, there is something deeply poetic about the fact that some mysteries may never be solved. The idea that the universe may not have an edge, or that reality itself might be a holographic projection, or that time could be an emergent property rather than a fundamental dimension. These are not just scientific challenges, they are reminders of the beauty of the unknown. Not knowing is not a failure, it is an invitation to wonder, to imagine, to dream. There is a delicate balance between knowledge and mystery, one that keeps the flame of curiosity alive. If all questions were answered, if all secrets were revealed, would we lose the very drive that makes us human? Perhaps the true purpose of exploration is not to conquer the unknown, but to learn to live in awe of it. As we continue our journey into the cosmos, we must remember that the universe is not just something to be studied, it is something to be felt, something that stirs something deep within us. The sight of Saturn's rings through a telescope, the first images of a black hole's event horizon, the realization that every atom in our bodies was forged in the heart of a dying star. These are not just scientific facts, but deeply emotional experiences that connect us to the grand narrative of existence. They remind us that, despite the vastness of space, we are part of something far greater than ourselves. So, what is the ultimate lesson that cosmic exploration offers? That our significance is not measured by our size or our place in the universe, but by our ability to ask questions, to seek meaning, and to embrace the mysteries that surround us. That the greatest discoveries are not just those that provide answers, but those that inspire new questions. And that the true value of the unknown is not in its resolution, but in the way it challenges us to think beyond what we know, to dream beyond what we see, and to reach beyond what we believe is possible. As humanity ventures deeper into the cosmos, uncovering mysteries both profound and perplexing, we are faced with a fundamental choice. Should we strive to close every question, seeking absolute knowledge, or is there inherent value in leaving some mysteries open-ended? Throughout history, every major scientific breakthrough has answered one question while simultaneously opening the door to countless others, an endless cycle that suggests that the pursuit of knowledge itself is more important than any single answer we might find. The universe, in its vastness and complexity, seems to defy final conclusions. Every discovery reshapes our understanding, challenging our assumptions and expanding our sense of what is possible. The idea that some questions may never be fully answered is not a failure of science, but rather a recognition of the limitless nature of exploration. If we were to reach a definitive endpoint in our understanding of the universe, what would remain for future generations to discover? The beauty of science lies not just in the answers, but in the process of asking, of wondering, of imagining, of seeking something greater than ourselves. There's a poetic elegance in leaving the mystery open, in acknowledging that while we may never grasp the entirety of reality, the journey itself is what defines us. The greatest revelations in cosmology have all been moments of profound realization, yet they have never truly been endings. The discovery that the Earth is not the center of the universe led to deeper questions about our place in the cosmos. The realization that the universe is expanding forced us to ask what lies beyond its observable limits. The detection of dark matter and dark energy has left us grappling with forces that we do not yet understand. Theories of the multiverse, of holographic space-time, of quantum gravity. Each of these represents a doorway to an entirely new way of thinking, rather than a final answer. This endless progression of knowledge suggests that perhaps the universe itself is structured in such a way that it will always remain just beyond our full comprehension. If space is infinite, then so too are the questions we can ask about it. If time is emergent rather than fundamental, then our very notion of finality may be an illusion. If reality is shaped by quantum probabilities, then there may be no single, absolute truth, only an evolving landscape of possibilities, shifting as we deepen our understanding. In many ways, leaving the mystery open-ended reflects a deeper philosophical truth, that meaning is not something imposed by the universe, but something we create through our own curiosity and exploration. Just as no single scientific discovery defines the entirety of human knowledge, no ultimate conclusion is necessary to justify the pursuit itself. The value of space exploration, of cosmology, of theoretical physics, lies not in reaching a final answer, but in the endless expansion of thought that it provokes. Summary of the biggest takeaways. Curiosity is the engine of progress. The more we learn about the universe, the more questions arise. Every answer leads to new frontiers of discovery. The unknown is not something to be feared, but embraced. The greatest moments in science have come from challenging assumptions and venturing into the unknown. The nature of reality may be far stranger than we ever imagined. Whether through the multiverse, the holographic principle, or quantum gravity, the cosmos continuously defies our expectations. Humanity is united by the pursuit of knowledge. Regardless of nationality, background, or belief system, the desire to understand the universe is a common thread that connects us all. Mystery has value in itself. The universe does not need to be fully understood for it to inspire awe, wonder, and meaning in our lives. Final thoughts on the infinite possibilities of space. As we stand at the edge of what is known, looking out into the abyss of deep space, we must accept that some mysteries may remain forever beyond our reach. This is not a limitation, it is an invitation. The infinite nature of space reflects the infinite potential of human thought, of imagination, of discovery. There will always be new questions to ask, new theories to explore, new ways to push the boundaries of what we believe is possible. Perhaps the ultimate lesson of the universe is that it was never meant to be fully known, only endlessly explored. And in that, we find our purpose not in closing the book on cosmic mysteries, but in ensuring that the story never truly ends.